Okay, thank you very much for the invitation to give the talk. I will start with a very broad introduction into turbulence and then go to the outer planets and then at the end with Juno. I'd like to start with hydrodynamic turbulence. And turbulence is a property of fluids and of the movement of fluids. And if the flow of a fluid is highly dynamic, non-laminar, and chaotic, then it's often loosely called turbulence. And a very prominent example of such a turbulent flow you can see if you take a boat tour and you stand at the rear of the ship, look into the wake, and then you see this kind of turbulence. And let's zoom in into the turbulence, and you can see here like a chaotic type of flow. And one of the key ingredients of the turbulence are eddies or vorticities or swirls, and you can see here big eddies, you see small eddies, all different kinds of eddies, and that's the building block of turbulence. And on the size of the ship, very large eddies are generated by the movement of the ship in the water that perturbs the flow. And then the biggest eddies are here L0. And by advection of the water of the eddies, they grind on each other, break up to smaller eddies. The smaller eddies do the same. They interact with each other by advection, break up into smaller eddies. And this is the essential building block of turbulence. That's the turbulent cascade getting any energy in the flow, kinetic energy, to smaller and smaller scales. And at the smaller scales, then viscosity sets in and dissipates, converts that mechanical energy into dissipation. And what's very important is that the energy transfer here from the bigger scale to the smaller scales, that's without loss. Here energy is conserved, and only energy in the mechanical flow is conserved, and only at the larger scales it's dissipated. And so turbulence is basically like a grinder that grinds down eddies to smaller scales, and the smaller scales, sort of the eddy then can be eaten because they're too big to eat at the larger scales. And what's typically done in turbulence theory is sort of measuring the energy or the power in the eddies as a function of eddy size. And turbulent theory likes to use, instead of eddy size, wave number. So that's the inverse. And you can see here, that's wave number, the logarithm, and here energy in the eddies. Here are the smallest eddies, and here are the largest eddies, and here are the smallest eddies. And this is sort of basically the size of the ship. The eddies are generated, then they break up to smaller and smaller eddies, and the energy in these eddies then gets smaller, but itself similar, and a slope in log space is observed. So it's a power law with the spectral index of minus 5/3, how the energy in the eddies decrease as a function of eddies size. And this minus 5/3, that's called the Kolmogorov spectral index, and that's universal in all different types of hydrodynamic flows. And at the smaller scales, the energy is then dissipated into heat. A dimensionless number called Reynolds number, that's the advection term divided by the viscosity term. That's used to indicate if it's turbulent or not, and if the Reynolds number in hydrodynamic flow is larger than roughly 2000, then the flow usually assumes turbulent properties. Now, I'd like to jump to turbulence and plasmas, and I first like to demonstrate that plasmas can be actually turbulent, and it's not a crazy idea of theoretical physicists from Russia or Princeton University. And here is a movie of turbulence that's observed by the stereo spacecraft, and that's observations of plasma. Here it's Comet Encke, and you can see here the tail of the comet. It's basically like the comet is the ship in the solar wind. And you can see here, it's a highly non-laminar turbulent flow that develops in the wake of the comet. And in plasma turbulence, there are actually two types of Reynolds numbers. There's the regular Reynolds numbers, that's the advection term divided by viscosity, but there's another avenue how energy can be dissipated, and that's resistivity, and so that's described by the magnetic Reynolds numbers, where it's the induction term divided by by the diffusivity, by the magnetic diffusivity. And if you calculate these numbers in the solar wind and magnetosphere, then usually 10 to the power of 5 up to 10 to the power of 10. And so these are Reynolds numbers where we're clearly in the turbulent regime. And now I'd like to discuss primary differences between hydrodynamic turbulence and plasma turbulence. And one of the biggest differences is that we have an additional force in plasma, that's the electromagnetic force. So even in incompressible plasmas, we still have two, on the larger scale, two wave modes. That's the shear Alfvén mode and the degenerated slow mode. And so properties or perturbation will always propagate. And so this is the building block of plasma turbulence, is then not eddies grinding on each other, but wave packages being propagated and wave packages that collide and then nonlinear interact and break down to smaller wave packages. And that's been observed and simulated like millions of times. And here's, for example, in a plasma lab, like Alfvén wave packages that generated on two sides crash into each other, and then they observe that they break down to smaller scales. So the building block is the interaction of wave packages. And another key difference between plasmas and hydrodynamic flows is that plasmas consist at least of two species, ions and electrons, with vastly different inertia. So that's why we have different sort of spatial regimes where turbulence can occur and different turbulent cascades. So here on the larger scale, that's L0, that's the size of the ship, the size of the comet, or the size of the sun. Energy is injected, the wave packages break down to smaller scales, and in the MHD regime, we also have a -5/3 spectral index. Then if we come to ion scales, that's either the ion inertial length scales or the ion gyro radius, ion kinetic effect sets in, and we get a different cascade. That's usually very often a kinetic Alfvén wave cascade is observed, for example, in the solar wind with the spectral index of -7/3. And then if we come to electron scales, that's either the electron inertial length scales or the electron gyro radius, then electron kinetic effect sets in, and we can have another cascade, or we can have exponential damping. And now with these are like the two main plasmas, and we have the electromagnetic forces, meaning it's always waves. And with that picture, I'd like to go to Jupiter. Here's Jupiter's magnetic field lines, and the magnetosphere is constantly perturbed, for example, by radial mass transport, which we just saw. And then we have wave packages that communicate between the plasma sheet and, for example, Jupiter's ionosphere. The wave packages then are reflected at boundaries, like the ionosphere or other gradients. And then we have other wave packages. And when these wave packages intersect, then the turbulence starts. Then cut up or broken up to smaller scales, and we have smaller wave packages. These wave packages travel along the field lines, interact with other wave packages, and this is what creates a turbulent cascade. And what a key difference between the solar wind and turbulence in the magnetospheres of the outer planets is that we have a strong background magnetic field, like within the middle magnetosphere, for example, of Jupiter. So the wave packages are always traveling along a given guiding field. So they do not change the topology of the system, but they are waves that are within the topology of the large scale field. And after we discussed these ideas, then now I'd like to show you that in the magnetospheres of the outer planets, there are really turbulent fluctuations. And here, that's a day in Saturn's magnetosphere, observed with the Cassini spacecraft. You can see here all three different magnetic field fluctuation components. And you can see here on top of the background magnetic field, there's small scale magnetic field fluctuation on different scales, different size. And they are what we think the result of a turbulent cascade, all different sizes of wave packages. And if you calculate the power spectrum of this time series, then you get what expected from turbulence here. That's the frequency, and this is the power density and the fluctuation. Here are the ion scales. And this kinetic ion scales, we have a spectral index of 2.6. That's a little larger than what we expect from kinetic Arcane waves. That's discussed in the literature, what could steepen them, or it could be also Whistler waves. And at scales below the ion cycle, below the ion scales, we have here a spectral index that's very consistent with the -5/3, which we expect from an MHD turbulent cascade. This was Saturn. Jupiter is seen the same. That's a paper by Tao et al. Below or at frequency higher than the ion scales and the ion kinetic scales. We have the spectral index of -2.5, close to 2.3. There's a steepening effect maybe of the kinetic Arcane waves. And then we have an MHD turbulent cascade, which in the Jupiter system appears to be variable. When we started to look at turbulence, we also looked at the amplitude of the turbulent fluctuation. And in Jupiter's magnetosphere, we see that they sort of maximize between 15 to 30 RJ. This is where the corrotation breaks down. And we think like the breakdown of the corrotation of these wave packages, because they communicate information and momentum between Jupiter's ionosphere and the plasma sheet. And this is then the root cause of the turbulence. The turbulence also have, no, that was sort of the process of the turbulence and the cascade themselves, but they have major implication because they chop up the energy to smaller scales, where the energy then can be converted into other forms of energy, into heating or acceleration of electrons. And then we studied where in Jupiter's magnetosphere are conditions fulfilled so that the energy in the waves packages can be converted into other forms, irreversible in other forms of energies. And then we find the inner middle magnetosphere, the dominating length scales is the electron inertial length scales. And this is sort of biggest just above Jupiter's auroral region. And so Landau damping is therefore expected to play a major role in damping and converting wave energy into electron energy. And at larger distance, cyclotron damping is expected to play a major role, like in the plasma sheet. And if we apply turbulent theories, now I jumped too far, apply turbulent theories and calculate the heating rates, and we do that, for example, for Jupiter, then the turbulent heating is powerful enough to solve the heating problem of Jupiter's magnetosphere. Here, the dotted line are measurements of the temperature in Jupiter's magnetosphere. You see the temperature increases as a function of radial distance, while without energy source and expanding magnetosphere, it would adiabatically cool. And but the turbulent heating, that's the solid line, is consistent with the observation. Similar conclusions also have been reached by Inge and colleagues. Also, that's here for Saturn, but they also applied it for Jupiter. Also, with they differ a little bit, like in the transport models, but primarily the primary conclusion is that the heating of the turbulent fluctuations is sufficient to heat the magnetosphere to observed values. And this is now in the equatorial plane. Now, at the high latitudes where Juno is making the crucial contribution, and the Juno spacecraft passed now multiple times over the main aurora, so we have in situ measurements of fields and particles above the auroral acceleration region or in the auroral acceleration region. And then magnetic field fluctuation also have been observed there, either over the aurora or in the footprint tails of the moons. And you can see here magnetic field fluctuations, which appear to be turbulent fluctuations. They are perpendicular to the background magnetic field, have been observed, and when power spectral densities are calculated, they are consistent with ion turbulence in the ion kinetic regimes here, -2.3. It's also been observed at little smaller latitudes by Loch et al. And you can see here also transverse fluctuations are strong, compressible fluctuations are weak. That speaks for Arcane wave or kinetic Arcane waves. So they are present, and the wave-particle interaction of these waves appears to be playing a major role in contributing to auroral electrons. And the acceleration process I do not cover because Bob covered that great yesterday. And now I'd like to come towards the end to like one of the really more complicated problems. That's a third difference between hydrodynamic and plasma turbulence. That's the anisotropy, because there's a magnetic field present in plasmas. Then we have the J cross B force. That's the primary force that acts on the flow. That's perpendicular to the background magnetic field. So there's a basic anisotropy in the system. And if we look here at wave packages, which are here illustrated by these shapes, and the lines are background magnetic field, then because of the J cross B force, the breaking down of the eddies is mostly perpendicular to the magnetic field. So they break down, they get smaller, the eddies perpendicular to the magnetic field. So that means they change their shape. At the same time, they are also reduced a little bit like in the length, but the turbulent cascade makes originally round wave packages more and more elongated, and at the end, after multiple cascade cycles, they end up like as extremely long spaghettis. And this is then different to hydrodynamic turbulence. This is just the beginning. At the end, they will be really long spaghetti wave packages. And there's a theory that sort of calculates the shape of these wave packages. They're called critical balance. That's Goldreich and Schroeder. That's the same Goldreich with the unipolar inductor model. And this is sort of the idea behind it, that during a nonlinear interaction, an eddy shapes a scale perpendicular to the magnetic field while it travels with the affine velocity along the magnetic field, and sort of that determines the shape of the wave packages. Now we go to Fourier space again, and in Fourier space, so the spaghettis are the opposite. So they are, that's the length, and that's perpendicular to it. So, so they are D-shaped in Fourier space in the other direction. And the critical balance translates to Fourier space in this expression. This is probably, the critical balance, how it's mostly known. And now this is important because it tells us how K space is populated with energy. And this is K perpendicular. This is K parallel always parallel to the background magnetic field. So this is our ship that generates fluctuations. And then the cascade is basically perpendicular to the magnetic field. So the eddies get smaller and smaller in this direction, and K perpendicular gets larger. At the same time, it fans out towards the critical balance line, and this is here. And then we end up with K space being populated only in this area. There's no power in this part of K space, assuming critical balance. And it's that appears to be like the leading theory in turbulence. And this is very important because usually spacecraft measure time series. You convert that into frequency spectrum, but that's what we have. We do not measure directly K space or real space with only one spacecraft. And if their theory exists for K space population, then a moving spacecraft also is the wave vectors are Doppler shifted either by the velocity of the spacecraft, or if it's aphanic propagation, it could be also the aphanic propagation here. With these two velocities, any wave number K is mapped into a frequency space to meet that delta condition. And so what it means is that many different Ks can contribute to one single F. And to more easily see that here, that's K space, K perpendicular, K parallel, and this is one frequency. Like the orange line, the green line is one frequency. And so all the K vectors along this orange line contribute to this exactly one frequency. And so it's really then important where the power lies. If the power lies here, then only these K vectors contribute to this frequency. If the power would lie here, then one frequency would see a totally different spectrum. And here that's calculated for the EO flux tube, our model. And this is here the critical balance line, and the power is below the critical balance. And for this model of the EO flux tube, we see that frequency measurements, that's one frequency, that's another frequency. So this frequency scans the perpendicular wave vector space and not the parallel wave vector space. And this is very important for interpreting measurements. Okay. Here, that's the EO footprint tail, Murray et al. And this is here measurements of the magnetic field. These are here the magnetometer. Here, that's the wave instrument. That's first been published by Ali. And if we take a kinetic Arcane wave turbulence and interpret it as a perpendicular spectrum, then we would expect kinetic Arcane wave turbulence. That's -7/3, and that fits perfectly to the data. And it's actually not surprising to see kinetic Arcane wave turbulence in EOS Arcane waves. But if it's not being interpreted as a K perpendicular spectrum, then it would be a totally different physics. And so that's why it's very important to know, to have a model for K-space, and that's a non-unique problem, but you can only interpret frequency spectrum if you have an underlying idea or the underlying physical expectation for K-space because of the complicated relationship between K-space and frequency space in a moving spacecraft. And so now I'm at the end. What I wanted to show is hydrodynamic turbulence is eddy interaction. By advection, plasma turbulence, there are a couple of things which are different. It's wave packages interaction because we have wave packages that propagate even in the incompressible limit. Then we have multiple cascades because we have different scales in plasma. We have an ion turbulent cascade, we have an ion kinetic, and an electron kinetic cascade. And then we have many pathways of dissipation. Dissipation is usually through wave particle interaction. There's a multitude of resonant and non-resonant wave particle mechanisms. So there is a much larger possibility of how energy is irreversibly converted into heat and particle acceleration in plasmas. And we have the anisotropy due to the existence of a background magnetic field. And the turbulence in the magnetospheres of the outer planets. The small-scale magnetic field fluctuation in these magnetospheres are consistent with the turbulent cascade and turbulence shaping these fluctuations, and they appear to play a major role because their dissipation can significantly contribute to the heating of the magnetospheres and maybe appear to be a major role in wave-particle interaction for accelerating electrons and maybe also ions. What I didn't cover in my talk, I apologize for that, magnetosheath and magnetotail turbulence, because then I would do a little bit of everything and nothing comes out. So maybe next MOP somebody else talks about magnetosheath and magnetotail turbulence, and here are people who worked on these two areas. Thank you.